another story, something to get off my chest.
Hello and welcome to another Pyperpod. Today we're going to look at urinary physiology, and most importantly we're going to look at the homeostatic relationship that the renal system has in essentially controlling a lot of our balances, our blood pressure, our electrolyte balances, acid-base balances. So we're going to go through focusing a lot on the nephron itself and looking at how different aspects of the body help regulate these functions. So first of all, a bit of an overview. The renal system, and in particular the urinary filtration aspect, is responsible for the filtration of all plasma, separation of waste, but also the reabsorption and elimination of certain substances depending on what the body needs. And with that, it obviously controls our blood volume and takes care of our osmolarity that we hold within our cells. The kidney also produces a couple of hormones, so renin, which we'll talk a little bit more about in the regulation of blood pressure, erythropoietin, responsible for the formation of red blood cells, and calcitroin, which is essentially our vitamin D steroid hormone. On top of that, the kidney is our main metabolic organ that's responsible in regulating acid base, and it's also really useful at detoxifying. If your body has a whole bunch of free radicals or essentially broken down cellular structure or certain medications, it's the kidneys that's responsible for the detoxification and the secretion of those substances from our body. So when you look at urine formation, it essentially can be broken down into 4 different steps. And obviously we'll go through each step in details, but just as a means of overview, we have our there we go through tubular reabsorption and tubular secretion, pretty much within the same structures, and then we finish at concentration, which is essentially where we decide whether or not we want to keep the water in there or remove the existing water that's in place. And that's essentially the whole process, and this is what takes place in the nephron itself that's found in the kidney. So let's break each one of those steps down, and then we'll bring in a little bit of electrolyte and acid-based knowledge as we need to. So the first step is glomerulus filtration. Now this is highly dependent on your high hydrostatic pressure. So as the blood comes in through the arterioles within the kidneys themselves, it comes in under a massive hydrostatic pressure. Now when the fluid and the solutes get pushed through under that hydrostatic pressure, we have a low osmotic pressure present in the fluid that's pushed through, because large molecules like blood cells and proteins can't be pushed through. Okay, so they're too big to be pushed through, which essentially gives us our low osmotic draw on the inside and our high hydrostatic pressure on the inside. Now what keeps the water and the solutes within the capsule itself is the capsule has its own osmotic pressure, which essentially doesn't allow any reabsorption of fluid or solutes within the Bowman's capsule itself. Okay, so essentially anything smaller than our 3 units in size will pass freely through the membrane. As you can see the picture to the right, it's a highly fenestrated structure that allows fluid and solutes to pass freely through it under pressure, and that's essentially what happens first at our glomerulus filtration, right at the edge of the Bowman's capsule. So when we look at a glomerulus filtration rate, it essentially means the amount of rate that amount of fluid that passes through the actual glomerulus. So therefore the amount of fluid that is actually produced per minute is what the glomerulus filtration rate is. Now on average you should have about 120 mils of fluid passing through the glomerulus every minute. Now that doesn't mean there's 125 mils of urine that's going to be produced per minute, obviously, otherwise we'd do nothing but live on the toilet. But that's the amount of plasma-based fluid that passes through the glomerulus in any minute. So that means the average person has about 180 litres of fluid passed into their kidneys each day. Now, in a normal state, normal healthy body, on average, 99% of everything that is pushed through is reabsorbed, which means anywhere between 1 to 2 litres of urine is produced a day. Now, at the glomerulus itself, it has some very clever structures surrounding it, very specialized chemical receptors and barorecepting cells around the glomerulus head that allows the renal to actually auto-regulate based on the pressure coming in. So if the arterial pressure is anywhere between 75 and 175 millimeters of mercury, the actual glomerulus structure can alter the amount of blood that comes in by either opening up the vessels, allowing more blood flow through in times of low blood pressure, or reducing the amount of blood that will actually come through in times of high blood pressure. Because obviously if the high blood pressure was able to bust through, then essentially it will cause destruction and you'll get a whole bunch of different lot more proteins basically would come through, and then blood would come through, that sort of thing. Same too, if the blood pressure was too low, then your hydrostatic pressure wouldn't be high enough in order to push the fluids through. So it's not perfect. You can obviously have things like pre-renal failure and destruction, but it does have its own internal auto-regulatory system that controls the amount of blood flow that comes into the glomerulus head, just for your knowledge. Okay, so once all the fluid is pushed in to the kidney, then we start our reabsorption process. Now, the proximal convoluted tubules are the main area in which reabsorption and excretion occurs. Okay, so 65% of all the filtrates that have been pushed through are returned to the blood within the proximal tubule area itself. Okay, so a vast majority. Now, this area, like most of them, is essentially held together by epithelial cells, just really small epithelial cells, and they have a lot of microvilli within them too. Now, this sort of helps facilitate movement of the fluid, but it also contains specialized protein structures that allow for reabsorption that we'll look into in just a little bit. So the main factors working on the actual proximal end is osmosis. So obviously when we look at osmosis, we're talking about the concentration of solutes. Okay, so if we have something that's low osmotic value, so therefore it has a low osmotic draw, it's not going to have any pulling power towards it, whereas something that has a high osmotic draw is going to draw fluids into it. Okay, so when something is low osmolarity, it generally means that it's high in water concentration, and if it's a high osmolarity, it's generally low in water concentration. So your osmotic pressure is associated with drawing power. Now I just wanted to bring that up quickly because that's essentially what the main aspect of the proximal tubules and the subsequent structures work on when we're dealing with reabsorption and secretion sometimes. So it's the solvent drag that essentially allows for most of the water and solvents to be absorbed in the proximal tubules. So if you think about the glomerulus head as it pushes through, it is going to get rid of a lot of water and a lot of small solutes themselves. Okay, your electrolytes, your glucose, amino acids, nitrogenesis weights, they're all very small structures. What's going to stay in the blood itself is a whole bunch of albumin, proteins, globules, large protein, which essentially will give the blood around the actual capillaries within the nephrons themselves a high colloid osmotic pressure. And what that will do is it will physically draw water via osmosis from the tubules back into the bloodstream. Okay, so that's where most of the absorption factors come from. But there are a lot more specialized structures that occur, especially within the proximal head, that we'll talk about. But this is just the main drawing power. The other transporters within the proximal head is our active transport of sodium. So sodium channels with the sodium-potassium pump are activated in the proximal tubules as well. So that will use energy in order to essentially push sodium into the bloodstream itself. Now, believe it or not, the kidneys are responsible, during rest anyway, in using about 20 to 25% of our oxygen that we breathe in. Okay, so the kidneys use a lot of oxygen because they need a lot of energy when dealing with active transport. Okay, now a lot of the reabsorption of specialized molecules is done by active transport, and a lot of the secretions are done by active transport as well. So a lot of energy is used. Therefore, at rest, we need a lot of oxygen as well. So, sodium-potassium pump occurs, and the cool thing about the sodium-potassium pump is because we have secondary active transport of other nutrients, is we have specialized protein structures on the microvilli that essentially allow glucose, amino acids, and other nutrients like calcium, things like that, to piggyback on the sodium itself. So it piggybacks onto the sodium line with the specialized protein, and it actively transports glucose, amino acids, and other nutrients. So it is not normal to find glucose and amino acids within, or proteins within, the actual urine itself. Okay, because of this secondary active transport piggybacking that occurs. Now, if you do end up finding them in the urine, it means that essentially it's exceeded what's known as your total reabsorption value that can occur. So essentially with glucose, if it's anything over 10 millimoles of glucose that is secreted through, then it can only pick up so much. There's only so many transport channels available, meaning some of the glucose is going to get through. So that's basically how we end up with these things in our urine. Now, because of this sodium active transport and this other secondary active transports that's occurring, this is going to actually encourage additional osmosis. Okay? Because sodium is the electrolyte with the biggest osmotic draw, calcium amino acids also have some as well as glucose. We're going to draw fluid with those active transport molecules as well. Okay, so the electrolytes will actually draw fluid, which is essentially osmosis as well. On top of that, because of all these cations that are being absorbed, mostly sodium, we're actually going to get absorption of anions like chloride because of the electrostatic attraction between negative anions associated with cation draw. Okay, that's something known as, the J drift. So obviously you got your osmotic draw, but then you also have your opposing electrostatic attraction as well. On top of that, I know we've gone through a lot, but on top of that, in the event that a protein or a hormone or enzyme or something like that, if you have larger structures or larger solutes that are found within the tubules themselves, then the actual area can go through endocytosis, so actually capsulize that particular protein and bring it back into the blood itself. So all very specialized structures. Okay, once we finish the proximal tubules, the urine heads down the loop of Henle. Now essentially the loop of Henle is broken up into two different areas, and essentially the thickness of those areas alter as you're going along. So the main purpose of the loop of Henle is to increase the ionized concentration values that is found within the blood itself. Okay, so the descending loop of Henle allows for osmosis of water based on purely osmotic gradients, but the thick ascending side of the loop of Henle doesn't allow for water, and it actively pushes out salts into the actual environment, into the extracellular fluid surrounding it, creating a high osmotic value on the outside, and what that does is it allows for concentration of the urine later on when we get to the collecting ducts themselves. So that's the purpose of the Looper Henley, is essentially to overload, if you will, the concentration of solutes within the extracellular fluid next to the collecting ducts, which we'll talk about later on. Now once we get to the distal tubules, most of the fluid and the solutes have been absorbed, but it still has about 20% of the water and 10% of the solutes that are left from the original glomerulus filtration rate. Now the difference between the distal tubules compared to the proximal tubules is that this area here is subject to hormonal control. So it's the hormones within our body that essentially will regulate additional uptake of water, sodium, potassium, whatever it may be. It's the hormonal control that will occur. Now, like the proximal tubule, this is also the place that a lot of wastes are essentially being excreted in as well. But just to have a look at the hormonal control of the distal tubules, we obviously have aldosterone. Now, aldosterone is essentially activated by a few things. So it's activated by the renin-angiotensin aldosterone pathway. So in the presence of a low blood pressure or a activation of reduction in stretch fibers, things like that will release renin, angiotensin 2, and then aldosterone can be released. It can also be released in a response to chemoreceptors if it picks up a reduction in sodium concentration or an increase in potassium concentration within the blood. So what aldosterone will do in the distal tubules, it will increase the amount of sodium and therefore water that is absorbed in the distal tubules, but it will also push in potassium to be secreted as part of the solutes. So that obviously helps regulate sodium levels, regulates potassium levels, and obviously maintains our volume and blood pressure. Now, it's true, if we have too much sodium, then the atrial natriuretic peptide kicks in, and that comes from the myocardium, and it's usually associated with high blood pressure, with sodium having such a high osmotic draw. This peptide essentially increases the amount of sodium, and therefore water, that stays in and is excreted by the body. So both of those control the distal tubules associated with absorption. Now, when we look at secretions, we just need to look at that first, because essentially it happens mostly in the proximal tubules and the distal tubules. Now, the secretion of chemicals is essentially can be done via concentration gradients, and can also be done via active transport. So your nitrogenous waste, like your urea, your uric acid, essentially will be moved into mostly be moved into the filtrates in order to be excreted. Okay, other things like your creatine will also be excreted, and any form of other waste products. Okay, this is also where a higher concentration of drugs, so once drugs have been metabolized and they have waste products, this is essentially where these will be excreted as well. Now, on top of that, this is also the areas which helps regulate our acid-base balance. Okay, so the secretion of a certain acid-base substance obviously goes hand in hand with the absorption of another, but it essentially is controlled by the kidneys itself. So just having a closer look at that, we'll look at what happens in the body if essentially obviously one of our gas that can travel within our plasma itself, so it can get passed through into the kidney. Now I know there's not a lot of CO2 that's in the kidney. Sorry, that's been in the blood, only about 1.5%, but it can be passed through. Now that combines with the CO2 that is already being produced by the metabolic energy production within the Krebs cycle. So they bind together. And it goes through the formation of carbonic acid with the aid of our carbonic anhydrolase. Now from there, obviously, it goes through its dissociation process where it becomes a hydrogen ion and a bicarbonate ion from there. Now in the case of acidosis, what happens is the body will excrete extra hydrogen ions and with it a chloride, and essentially it will push out a bicarbonate ion and a sodium ion into the extracellular fluid in order to act as a bicarbonate buffer. Okay, so in the event of acidosis, the breakdown, hydrogen will be excreted with chloride and bicarbonate and sodium will be absorbed into the extracellular fluid to be picked up by the blood and used again as another buffer. Now obviously the opposite occurs when we're dealing with alkalosis. We still have the same substances, starting with our CO2 plus water making carbonic acid, breaking down into bicarbonate and hydrogen, but this time we remove just a bicarbonate ion into the tubular fluid, and we push a hydrogen ion and chloride into the extracellular fluid itself. Therefore, essentially being able to utilize and decrease the pH from its alkalotic state. Okay, so that's essentially what happens in the tubules themselves. So like I said, the proximal and the distal tubules have a strong role to play in our acid-base regulation. Okay, obviously in conjunction with our respiratory systems as well. Okay, finally, after all this noise and everything is done, we finally get to the collecting ducts. Now it's the collecting ducts that essentially will determine the concentration of our urine itself. So when we think about the collecting ducts, essentially we have what has been excreted into the extracellular fluid from a whole bunch of nephrons. Now this in turn obviously has a massive osmolarity value within the extracellular fluid because of the presence of sodium chloride and urea that has been pushed into the extracellular space. Okay, so that's there. So that will obviously have a huge driving power within the cortex of the collecting duct itself. Once we get down to the medullary aspect of the collecting ducts, so essentially just to define the difference, the cortex means the outer ring of your kidney itself, and then the cortex is the darker media part of it where the branch of the Lupus and the collecting duct will sit. Okay, so it's in this region that essentially the cellular structure of the collecting ducts change, and it's no longer permeable to sodium chloride, but it is permeable to water, but only in the presence or absence of antidiuretic hormone will actually determine how permeable the collecting ducts are. So when we look at our antidiuretic hormone, obviously it's produced in the posterior pituitary gland within the brain, and it's activated essentially on drive from what's known as the hypothalamic osmolytic regulator. And it's a very, very sensitive aspect of the hypothalamus. It essentially can pick up a 1 to 2% change in osmotic value within the blood, and essentially it activates your thirst receptors, but it also activates your antidiuretic hormone. So if you're fully hydrated, therefore in quite a dilute state, very low osmotic draw, then you will not secrete an antidiuretic hormone. Okay, and the absence of an antidiuretic hormone essentially means that the permeability of water is very low. Therefore, water stays in the collecting duct and is excreted via the urine. Now, if you're dehydrated, therefore your osmotic pressure is very high, then the brain will secrete, so the posterior pituitary gland will secrete a large amount of antidiuretic hormone, which increases the permeability and allows for water to be drawn out via osmosis, and the urine becomes more concentrated. And that's the final role and what determines our concentration of our urine right at the end of the process itself. So when we look at urine should be clear, shouldn't have any blood, it should have the smallest amount of protein, if not none, and any changes to this colour or smell or anything like that essentially could mean that there's some form of a solute within. If you produce too much, it's called polyuria. If you don't produce much, it's called oliguria, which essentially means that you're not producing a lot, and it could mean that your body is building up with extra toxins, essentially, which is obviously not the best. Now, when we look at the concentration of values that you'll find in urine, obviously our body is extremely selective. So there's certain things in our body that our body doesn't need a large amount of, but it produces a large amount as well. So urea is essentially a byproduct of protein metabolism. So therefore, and is also highly linked to ammonia and nitrogenous rate. So it's produced, it's found in the blood plasma, but pretty much all of it is secreted. Okay. Same with uric acid. Uric acid is generated by the breakdown of nucleic acid. Okay. Now, nucleic acid is essentially just means the genetic material. So once that gets broken down, it produces a uric acid, and that needs to be secreted as well. Creatine, very useful in creatine phosphate system, but we tend to produce and excrete a lot as our muscle, break down and get utilized throughout the day. So again, a lot of it can be excreted. Okay, and then we start looking at our electrolytes. Okay, we get a lot of potassium in our diets and in our essentially swapping of metabolic processes, but it needs to be tightly regulated. So generally speaking, on a normal day, normal process, we will actually excrete more potassium in the urine that is actually generally found within the blood. Okay, most of the potassium that you find will be found within the cell, meaning if any is leaking out through different metabolic processes, it is often removed and excreted. Now, the opposite occurs with our chloride, sodium, and potassium. Chloride, sodium, and protein. Large amounts of these are found in the actual blood itself, and we need them. Okay, proteins themselves can't get through the kidney, so very, very little actually gets taken out, and chloride and sodium essentially is supposed to be in the blood. Okay, it's actually what gives us a lot of our osmotic power and our osmotic draw, so therefore we hold on to a bunch of that. When we start looking at specialized structures like glucose and bicarbonate, on a normal day and a normal state, we want to keep our bicarbonate buffers. We want to keep as much glucose as we can. So normally you shouldn't have any of that found in your urine as well. Okay, that's the end of urinary physiology. Like I said, just a nice quick one on mostly the homeostatic relationship with urine production and waste removal. Hopefully you got something out of it. The next lesson on this purely is on homeostasis of the body and essentially pH regulation. I know we're touching on a lot, it's just basically bringing it all into one lesson. So until next time, take care.